Um, all right, so we'll be starting the talk for today. The talk for today will be by Elijah, and he will be taking us through constructing a. He will be taking us through constructing a
proof that the halting problem is not solvable. The halting function is uncomputable. Ultimately, is the ultimate goal. Okay. So I'm going to start with a bit of historical motivation for why we even care or why anyone cares. So, general question to the audience: has everyone taken bridge to abstract mathematics? Okay, does everyone here know what functions are, what computable and uncomputable stuff is? Cantor's diagonal argument. Okay, cool. Okay, cool. So the first section is going to be on this thing called the Entscheidungs problem. It's a big German word. So, as I'm sure we're all aware at this point, when we're talking about mathematics, we start with some axioms, and then we build off those axioms. So there are mathematicians who want to do this sort of process, but for all of mathematics, one of which was David Hilbert, who initiated Hilbert's program, which was essentially to formulate axioms to create axioms to formalize all of mathematics. And he wanted to ask 3 questions about such a system. One is completeness. 2 is consistency. And 3 is decidability. So completeness basically asks, suppose a statement P is true in the formal system. Does there exist a proof in the formal system that it's true? Consistency is just what it sounds like, is it possible to derive P and not P in the system? And then decidability asks for any mathematical statement P, is there some sort of algorithm that will take in any mathematical statement P and tell you if it's true or not automatically? And this is the question that Alonzo Church and Alan Turing were interested in and were formulating answers to. And this question, because it's basically asking for an algorithm, is sort of where the idea of computer science in the true sense comes from. So Alan Turing decided to tackle this question. And the answer is no, there is no such algorithm. And we will not be proving that is the case. But we will be talking about two things that he used to prove this, and what is really the origin of computer science, which is a Turing machine and we're going to be discussing the halting problem. So if you're wondering why we care about the halting problem, which I will explain soon, the answer is basically that it was a lemma for this, essentially. And then as a side effect, we have electronic computers now. So also, this was not narcissism on his part. In his paper, he called them abstract machines. We just call them Turing machines in his honor. So we continue now. That was just a bit of historical background for why we care. We continue now to part 2. So part 2 is, what is a Turing machine? Sorry, let me write in all capitals. What is a Turing machine? So right now, basically what we're talking about is computation. So let's think about that in the most basic sense. I want you to think back to when you were in 2nd grade and when you were in your math class, and how did you learn to add, multiply, subtract, divide? Your teacher just gave you a sheet of paper, and let's say you wanted to I don't know, multiply 12 by 34. She just gave you basically an algorithm, a little set of directions on what you do. And then the idea was that if you do I even remember how you do this? It's and you add them, right? So the idea is if you just do the directions, you'll get the right answer at the end. And that's sort of the intuitive idea of computation, is manipulating symbols according to some set of directions in order to get a result. And Turing used this intuition and said, okay, what's like a super generic version of computation that I can think up? And this is what he came up with. So a Turing machine can be thought of intuitively is like, imagine you have like an infinite strip of like tape. Let's say it's like, I don't know, an inch across. And it's cut up into squares. Well, not cut, but it's marked into squares like this. And on each square, there's either a 1 or a 0. And there's only finitely many ones. The Turing machine itself you can think of as right now as like a little machine, which we represent with a triangle. And what it consists of is basically states and instructions. So the Turing machine is always already in some particular state. It scans the square and looks at whether it's a 0 or a 1. And then depending on what it scans, it does some set of directions, and then it goes to another state. And when it runs out of new directions, it stops. And what we're going to do right now is actually construct a Turing machine.
And just for clarification, and importantly, it only sees the current state. It doesn't remember what happened.
Right, yeah.
Also, except unless if the algorithm actually makes you remember.
Well, but for Turing's original example, it was...
No, because you have states in the Turing machine, and you could assign states for memory.
Okay.
So it's like implicit memory. You remember it because you're in that state, which kind of.
But the triangle itself only sees directly
the triangle. Yes.
Mm-hmm. So the Turing machine we're going to create is we're going to create an addition Turing machine. So you give it two arguments, x and y, and then it gives you x plus y. So how do we input that onto this tape? So what we're going to do is, let's make it concrete first. Let's say 2 and 3, and then we're going to have it give us 5, just to make it concrete, so it's a bit easier. We're basically just going to use Cowley notation. So we have 2 ones in a row to represent 2 as the first argument, then a space, and then 3 ones in a row to represent the second argument being 3, and then followed by infinite zeros on either side. In the Turing machine, we're going to say starts here. That's just like notation. We always start here. And then we're going to end. How are we going to end? We want to end with 5 ones in a row, as like to say that our output was 5, and we're going to end on the leftmost one. So, oh, I forgot. I should have mentioned. There's 5 things that Turing machine can do. So it can print, erase, apropos mistake, go to the right 1 square, go 1 square to the left, and it can halt. So printing just means it looks, whatever's on, it just puts, it writes like a 1 on the current square that's looking at. Erasing just means it writes a 0. Going to the left and the right by 1 square just means literally moving on the tape. And then halting is just stopping. And if the Turing machine ever runs out of instructions at some point, it just stops automatically. So using these directions, how could we take this input and get this output? Well, here's the basic idea, and let me write this in red as like a proof, just like it's a proof of concept. We're going to like, so let's say we have like 0, 1, 1, 0, like this. So the first thing we're going to do is we're going to tell the Turing machine to erase this 1. Then we go to this 0, and we print a 1 here. And then you can see from that alone, we already have like 5 ones in a row. So in effect, you can sort of think of it, not literally, but in effect is like just moving the 1 into the space. And we go back here, and then we're done. So how might we do that? Well, now we're going to illustrate how you diagram a way to diagram a Turing machine. So we said the Turing machine consists of states, and each state has directions. So, and this will make sense in a second. We're going to write the states as numbers with in circles. So it's going to be like a graph, and then we're going to have arrows pointing to the states which indicate instructions. So to make this Turing machine, we're going to start at 1. You always start at 1, as one might expect. So the first thing we do want to say is like, remember we said we want to erase this 1. So we're going to do this. Okay, so how do we read this? This says you're in state 1. If you scan a 1, write a 0 and then go back to state 1. And that's sort of the general idea, is like you're in like the state QI, then then you have like something you scan, and then it's you have the direction, which is if you scan this, do that, and then you go to state QJ. That's sort of the general idea of like how this is supposed to work. Then we're gonna say in state 1, if you scan a 0, go to the right, and then we go to state 2. And in state 2, we just want to iterate through. We want to get to this 0, so we're just going to keep iterating through 1s until we get to 0, if that makes sense. So we're going to say if you scan a 1, just go to the right, and then this is just sort of a loop. We just said, so it's sort of like a while loop if you're done programming. It's like while you see 1, just keep going to the right. Then we go, it says if you scan a 0, print a 1, go to state 3. Now we want to go back to the left, remember? So we say if you scan a 1, go to the left. This is going to overshoot, so we're going to end up at this 0 here by following this direction. But like that's okay, because then we'll just say, and then if you scan a 0, just go to the right. And then go to 4. Notice that 4 has no arrows pointing in or out of it. There's no arrows pointing out of 4. So that means it's the final state, because there's no further directions. So we can do this step. I want to do this now step by step just to make sure we all get how you do it. So we have 0. Let's do 3 plus 2. That might be a bit more interesting. So let's follow it. We're starting here at state 1. So we say, if you scan a 1, just write a 0 and then go back to state 1. So that was the first step in the program. If you scan a 0, go to the right. And then we go to state 2. Then state 2 says if you scan a 1, go to the right. So we're going to keep doing that. You scan a 1, go to the right. And then it says if you scan a 0, print a 1, and then go to state 3. 3 says keep going to the right as long as you see a 1. Then we're going to hit 0. When you see a 0, go to the left in state 4, and then you're done. And this works in principle for any 2 arguments, and that's like, so it's a Turing machine that adds numbers. Adds 2 numbers and gives you the output. Now, you may have noticed that, I don't know why I'm gonna need this. You may have noticed that what this is defining, this is a function, right? So it takes in arguments and assigns them values to the arguments. So this is a function. So we're going to consider a certain sort of function. We're going to consider functions from, this actually isn't of that sort, but we're going to consider functions as So a function is effectively computable if, sorry about my handwriting. A function is effectively computable if for any like argument, you can get the value of the function by following step-by-step directions. And then Turing computability, if it's Turing computable, that just means it can be represented by a Turing machine. Now, I hope it's obvious that every Turing computable function is effectively computable. Turing's thesis is basically just that the converse is true, which is that any effectively computable function can be represented as a Turing machine. So in other words, anything that his thesis, which is actually unproven, but no one's found a stronger form of computation as of yet. His thesis, is most people think it's probably true. His thesis is that anything that could be computed in principle, there is some Turing machine that computes it, basically. So we said Turing machine, so I guess now we go to part 3. Give me a second. Let's erase this. Does everything I said make sense to everyone so far? Okay. So now, a question we might ask.
If this is too much of a tangent, then don't worry about it. But how did he write his thesis if he didn't, what did he
Well, first of all, his thesis isn't actually, that's like his thesis, but the actual paper was not really about that. Remember, it was about the decidability, which he did prove rigorously. Turing's thesis, people believe it to be true because no one has found a stronger form of computation. There are equivalent form of computations like Church's lambda calculus, but it's not stronger than Turing's, but it is different.
It's not like a PhD thesis. It's like
Yeah, like an idea.
It's like a conjecture, sort of. Like he conjectures that it's probably true. Yeah. 3. The existence of uncomputable functions. Let me see what I'm doing on time. This will be a bit of a lengthy segment. Okay, we're good. So, a natural question we might ask is, okay, so Turing machines are functions. Is every function a Turing machine? As you can probably guess from the title, the answer is no. In fact, not only is not every function a Turing machine, approximately like basically 0% of them are computable, and we're going to prove that. So the first thing, the proof is that there are we're going to prove that there's uncountably infinitely many uncomputable functions. And the proof is two-part. One is we prove that the number of functions in general is uncountably infinite. I'm sorry, let me be clear. We're limiting here specifically to functions of this sort. So from z plus to z plus with one argument. But I mean, that would still prove that there are uncomputable functions because those are functions. So the number of functions of that sort is uncountably infinite. And then we're going to prove the more interesting part, in my opinion, that there are only countably many Turing machines. And then do you all see how it follows from that then there's like uncountably infinitely many uncomputable functions? Okay. So the first step, honestly, I might not even write it. Like, I know I can if you guys want me to, but so you all know like Cantor's diagonal argument. It's like you suppose it's not true, then you like put it in a list and you go down the diagonal. Okay, so if you want to like, I'll just do it. It's fine. So theorem, there are uncountably infinitely many functions of this sort. So it's a proof by contradiction. Proof, suppose not. Then you can make a bijection from, you can arrange them in a list. So we'll do that. 1, 2, 3, so on. And then
it's just a list of positive numbers.
Yep. And then we're gonna say this is like the first thing we write here. So it's like I don't know, 1, 2, 3, 4, blah blah blah. So we're gonna say 1 goes to 1. So this is the identity function. 1 goes to 1, 2 goes to 2, 3 goes to 3, etc. And then we can do like 5, 5, 9, 0. We can't do that one. Sorry, 1. Then we can do like 2, 3, 11, a million, whatever. And then the idea is, as you know, like with Cantor, we just define a new function which we could call like, I don't know, f prime, f hat, sure, f hat. And then we define it by saying it's if you see a 1 here, you do like, I don't know, 9. And then if you see anything that's not 1, you do 1. And then by definition, that's not in the list. This is just like Cantor's diagonal argument. So therefore, by contradiction, the number of functions of this sort is uncountably infinite. It's just like Cantor's diagonal argument, basically. That's not the most interesting part. This part is the more interesting part, and we will now prove there are countably infinitely many Turing machines. And so I think this is cool. This shows basically we're going to prove that we can systematically arrange all possible computer programs into a list. So first thing we're going to consider, I'm going to prove it like, I'm going to go a little bit roundabout, but like you'll see how it works at the end. So like just hear me out. So consider this Turing machine. 3, 4, 2, Hope we can all read my handwriting. 0. 0 to the right. Then, so if you're wondering what this does, like what it does is not really, the particular Turing machine isn't relevant. This is just like sort of this is just to help us illustrate the point. But if you're wondering what it does, this Turing machine, you give it a number and then it just outputs 1. So it's just like, it's just sort of like the straight line, except not really, because it would be like, it's not defined on real numbers, but you get my point. So if you remember what we said this is a state, this is a state, this is what we scan, and then this is what we do. So what we're going to do is we're going to, instead of having this little diagram, we're going to write out the same information, but as a list of quadruples of symbols, if that makes sense. So let me write that out, and then I'll explain a bit more. Q4, hopefully I'm doing this correctly. Q3, S1. This next section might feel a little bit roundabout, but like, you'll see what I'm doing at the end. It'll make sense at the end. So what do these mean? So basically where we wrote a 1 before, we're writing S1, and where we wrote 0 before, we're writing S0. So that's what these means. This just means 0, this just means 1. The Q's represent states, and then R and L just mean what they meant before. So like, for example, this one, it's the same information. We're just writing it in a list. So this one just means, let me erase that. This one, so this is just, which one is that? So this quadruple just represents this bit of information. So this says if you scan if in state 1 you scan a 0, go to the right, go to state 3. And it's the same thing here. If in state 1, if you scan a 0, go to the right, go to state 3. So it's the same information, but just presented in a list. Okay. And we took the lowest numbered state to be the initial state, right? And then we're going to say the highest numbered state has to be the halting state. And we can say that because if it's not already true, you can just add a new state that make that a new highest state, make that the halting state, and then it'll do the same thing. Just have it point to that when you're done. Okay. Now we want to say, we're going to consider right now we're going to consider the first two symbols of each one of these quadruples. So this is QJSI. So let's say there's n states in general. So we're going to say that, okay, so J goes from 1 to n. I goes from 0 to 1. So basically what we're going to say is we want n times 2 quadruples. So we want, for every j and every I, we want a quadruple corresponding to that. So we want it, and we're also going to list in order. So we're going to do Q1 S0, Q1 S1, Q2 S0, Q2 S1, Q3 S0, so on until we go through all this. Now notice this is not the case here, but that's fine. You can just change. We can change that because basically what you would do is so which one are we missing? Q2 S1, that's what we're missing. So if in state 2 you scan a 1. So what do we write for that? So what you do to fix it is basically you just say, you make an arrow going from 2 to the halting state, and then we say, if you scan a 1, just write a 1, which basically is the same as just not really doing anything. It leaves it the same as I saw it, and then you say, just go to the halting state. So can you see how that doesn't really, can you all see how that doesn't really change anything about the nature of the Turing machine? It does the same thing. So in general, you can always just do something like that. So we can write it out like this. So we're gonna add one more in. Q2, S1, S1, Q4, What was the next? Where are the next two? Q3. S0. It's S1, Q4, Q3, S1, 0, Q4. Okay, cool. And now, notice actually, since we have it in order systematically, but you don't even need the first two bits of information, we'll just know it from what place it's in. Does that make sense? So we can just erase these. And also, do you guys see how, like, in principle, anything I'm doing right now, you could do with, like, any Turing machine? Okay, cool. Wait, shit. Yeah, my bad. My bad. I think it was S1, Q4, I think. Okay, cool. And now we're gonna we're gonna encode these with numbers now. Here's what we're gonna do. We're going to say, so we're gonna represent Qj by just J, right? So this is just gonna be 3, this is just gonna be 2, etc. And then we're gonna say S0, we're gonna encode as 1. S1, we're gonna encode as 2. Left is gonna be 3, and then right is gonna be 4. So then we're gonna write this as a set of numbers representing these symbols. So we're gonna have 4, 3, 2, 1, 2, 4, 3, 1, 2, 4, 1, 2, 4. Moments like this where I'm glad I have notes, because I would not remember this. This set of numbers, that is. Okay, cool. And now we're going to use, so if you ever seen like anything about the proof of Girls and completeness theorem, you'll know he uses like, he encode the fundamental theorem of arithmetic to encode propositions as like real positive integers. We're gonna do the same trick here. So we're gonna take, so how many are there? There's like 12? Yeah, there's 12 numbers. So we're gonna take the first 12 prime numbers in a row and use these as the exponents and then multiply them out. And then that gives you a unique positive integer that will correspond to this Turing machine. And the fact that it's unique matters. So what would it be for this? It'd be 2 times 4, 2 to the 4th times 3 to the 3rd times 5 times 7 squared. Do you want, I'll just it doesn't really, like the exact, that's the idea. So you sort of see how this would like, does everyone see how this gives you a unique number that corresponds to this Turing machine, everyone? Cool. So this means the set of all Turing machines, you can make a bijection from a subset of the positive integers to all Turing machines, which is just to say that it's countably infinite. So the number of Turing machines is countably infinite and can be written down systematically, which I think is a really cool proof. This was one of my favorite things I discovered while preparing this talk.
So why do we have to go into the Gödel numbering?
Because it shows you that all the Turing machines can be, you can make it's how you would prove that you can make a bijection from a subset of the positive integers to the set of all Turing machines by doing this. Right. And it will be useful later also for the halting function.
Could you not say, because so the number of states that a Turing machine can have is finite, right? For any Turing machine, it's finite.
Mm-hmm.
And the number of transition functions it can have is also finite.
Mm-hmm.
So if you take all of the Turing machines and all their possible states, and there's a bijection from the natural numbers to that. So just the states themselves are countable,
Mm-hmm.
and the transition functions themselves are countable. So you have a countable set, cross a countable set, which should be countable.
I mean, I imagine there are probably other ways to do it. Like, I mean, you could, yeah, I think you're right, because you could say just from the fact that, you could say just from this fact that is like proof. But first of all, this is cool, and I want to show it. It is cool. I will not let anyone tell me otherwise. Second of all, the fact that you can do this will be useful for the halting function later anyways, so it will come up in a second.
Yeah, so the numbers that you pick there, are those like, can you pick an arbitrary string of numbers to represent any Turing machine, or do they have to be specific, like?
At which step? Like this step?
Yeah.
I think as long as it's systematic, you could pick whatever you want, I guess, theoretically. I would be I assume. Okay, is there anything else I had for this section? No. And then also, so we proved it. We proved that there are uncountably infinitely many uncomputable functions. So actually, if you pick a function, the probability that it's going to be computable is 0, which is kind of cool. So now we get, how are we doing on time? Let's check on 1. Okay, cool. You might finish a little bit early, but that's fine. Okay, and now we get to our final section, the part we've all been waiting for. We will now be discussing the halting problem. The halting problem. Okay. So let us consider this function. Let me write in the middle. Let's consider this function, HMN. What does H do? So it takes in two arguments, M and N, where M is, so remember we just proved that every Turing machine corresponds to, you can systematically get a unique positive integer for that Turing machine. So this M is just the number for some Turing machine M. So it's an encoding of M. This is like, Aponith isn't here right now, but one of the reasons it mattered is because it lets you use Turing machines as inputs for functions if you have numbers that correspond to them. There he is. So Aponith, what I just said is that consider this function HMN. M, it takes in two arguments. M is, so we just said every Turing machine has a positive integer that corresponds uniquely to it. And the reason that matters is that let's just take this Turing machine M, and we say that little m is its corresponding number, and then we can use it as an input into this function h. And then n is just some number, basically. N is just a number. So what does h do exactly? Well, basically, h will give you 1 or 2, and let me make sure I get this right. Okay. Doesn't hold. Okay, so basically what this does is it takes in the Turing machine and the argument. So it's going to tell us if, like, I don't know if this is correct notation, let's just say it. Does m with argument n, does that program stop at some point? Because theoretically, like I'm sure you know, you can write, if you've ever done programming, you know you can write infinite loops, right? You could have a program that just keeps going forever and never stops. So this program basically tells you for some program, for some argument, will it stop at some point? And it gives you a 1 if the answer is yes, and a 2 if the answer is no. This is a perfectly valid function. Is it computable? The answer is no, it's not. Damn. You can't solve the Goldbach conjecture with it either. And you can't automate away math, which is what this was ultimately used to prove. Which I guess is a good news for mathematicians, I guess, actually. So you can thank Turing for that. And Church. Church actually did it first, but yeah, whatever. He's not as cool. He doesn't have a cool backstory like Turing. So theorem. I'll write in the middle. Theorem. The halting function is uncomputable. Okay, cool. So proof. How are we going to prove this? We're going to use proof by contradiction. So if you've ever done computer programming before, you'll know that like often programs are really like a bunch of smaller programs, and you just like put them together in a big program. So what we're going to do is we're going to assume that H is computable, and we're going to assume there's a Turing machine corresponding to it. Then we're going to consider two other Turing computable functions, C and D, which you'll see what they are. We're going to put them together into a big Turing machine, M. And then we're going to prove that M displays paradoxical behavior. So it'll give you both like two outputs at the same time. And then that can't happen, obviously. So it proved that H couldn't exist, because that was the only thing that was in question that led to the construction of M. Does that make sense, everyone? Okay. So we're going to consider these two Turing computable functions. So first we're going to consider C. C is a copying machine. That's what we're going to call it. Okay, cool, right? What does it do? So this is the input you give it. 1, 1, so on and so forth. Let's just stop there. And basically, it'll just give you two of these, basically, hence the name. So I'll give you I'll give you this. And it would do that for whatever I don't know, input number you give it. So if you give it 5, it'll give you, you can think of this as almost giving you giving you the order paired 3, 3, or n for whatever n you give it. And then we're going to consider this Turing machine, and this is a Turing computable function. We're going to consider this Turing machine D, and I'm going to write this one out for you. This is a Turing machine. And I'm going to actually draw you the diagram for this one. So what this one does is basically you give it a number, right? And if you give it the number 1, it goes on forever. If you give it anything bigger than a 1, it's going to stop. So here's how you can think of it. Let's say you gave it a 1. So you give it a 1 as the input. So it's going to say 1, you go to the right, okay? And then we're going to say, in say 2, if you see 0, you go to the left. And then this is just going to loop forever if you have a 1. Does that make sense? Okay, cool. And then if you have anything bigger than 1, so let's say a 2, so we're going to start here. If you see a 1, go to the right. If you see a 1, go to the left. And then we stop. So it just stops. It didn't do anything. So all it does is basically it just loops forever if it sees a 1, and then just stops without doing any, without really changing the string if it sees a 1. Okay. So can I erase this info? Do you need this? Okay. So we have C and D. So we're considering these 3 Turing machines, and we're assuming that H is a Turing machine. H is going to be just the Turing machine that computes the halting function, the halting function Turing machine. C, D, H. So now what we're going to do is we're going to make a big Turing machine by linking them together. How do we do that? So basically, and we're going to do it in this order. We're going to do C will go to H, will go to D. And then this whole thing is M. M is the big Turing machine, and these are its parts. So basically what it says is, you give it a number, it does the copying routine, and then it takes the 2 numbers that the copying machine did, it gives it to the halting Turing machine, and then that halting machine will give you a 1 or a 2, and then the dithering machine will run forever if it gives you a 1, and it'll give you a 2, and then it'll stop if you give it a 2, right? Now, do you remember the output for the halting machine? We said the halting machine will give you a 1 if you stop, and then a 2 if you don't stop. So let's just say, okay, let's say you give it, let's say you give M n as an input, then the copying machine is going to get output n, you can think of this. So n, we're going to see H will then take n as inputs. So it's going to consider n as the Turing machine whose number corresponds to n, and then n is just the input. So we'll say, does this Turing machine halt with this input or not? And then it's going to do 2 things. it's going to give a 1 if it does stop, and then a 2 if it doesn't stop. And it's going to give that to the dithering machine. And then the dithering machine, if you give it a 1, it's going to run forever, which I meant. And then if you give it a 2, it's going to stop. So basically, what M does, the big idea, basically, the big main idea, is M does the in terms of its halting behavior, it just does the opposite of what N does. So if it determines that N is going to run forever, it stops. M stops. And if N stops, then M runs forever. And maybe you can think what the next step we're going to do is. This is a Turing machine, and we're going to, yes, exactly. We're going to let M be the number corresponding, little m be the number corresponding to this Turing machine. And we run it into itself, so we have M. It outputs MM. Okay, and herein lies the contradiction. What does M do? Does it stop or not? Suppose M stops, then at the end, M is going to have to run forever. But if it runs forever here, then it's going to have to stop at the end. So either way, it's going to have to both stop and not stop at the same time. And clearly that can't happen, right? So these are both valid Turing functions. These are both valid. Hooking it up like this is valid. The only problematic aspect was the assumption that H was a valid Turing machine. So since H is what caused the problem, by contradiction, H does not exist. So therefore, we say that the halting function is uncomputable. Is that clear to everyone?
So you've essentially filtered out everything from Cantor's diagonalization until you have exactly what you just have the diagonal numbers.
Something like that, yeah.
No, I'm saying like because you could pass H, you could pass anything to H, but you decided to only pass the diagonal arguments, M, and that's why you reached the contradiction. You just skipped all those steps that are necessary.
Yeah. Any questions? All right, well, that's all I had for you guys. So